Hi, today we are going to continue with the lecture which is focused on the components that are present in a spectrophotometer. So in a spectrophotometer, we have to provide the light source. There are deuterium light source, there are tungsten lamp light source. So different type of the lamp will provide different region of the electromagnetic radiations which can be directed to the sample. In addition to the light source, there are also some slit present in the spectrometer. The slit is used to reduce the intensity of the light, or we say that the slit is used to control the intensity of the light. Following the slit, then we have the sample holder, the dispersing devices, the detector, and the display which present the outcome as a form of spectrum. Dispersive element is an element which separates light into its individual wavelength components, and sometimes it is also called diffraction grating. This is the appearance of the diffraction grating. Other than diffraction grating, we also came across the prism, which it is able to spread the white light into the rainbow color radiations. Okay, so other than the prism and diffraction grating, whereby the diffraction grating, it consists of many parallel scratches on the surface. So when the light directed to the diffraction grating, this diffraction grating, due to the presence of these parallel scratches, so it will be able to spread the radiations into the different individual wavelength radiations. So in addition to this prism and diffraction grating, there is another component which is known as monochromator. Okay, it is an optical device that separates polychromatic light, such as sunlight or the light coming from a lamp, into a range of individual wavelength, or we call it as the monochromatic light. The light of the desired wavelength band is then directed onto a sample, a detector, or other components of an optical system. So this monochromator allows a narrow band of the individual wavelength to be selected. So how does a monochromator works? A monochromator consists of a dispersive element, which is this component D here. Usually it is the grating. It has an entrance slit, component B, mirror C to produce a parallel beam, an exit slit F, and another mirror E. So A is the light source. Light is focused onto an entrance slit, and then it is collimated by a curved mirror C. The collimated beam is diffracted from a rotatable grating D, and this grating, it can rotate at different angle. Once the light hit the grating, it will disperse the light into the individual wavelength, and the dispersed beam refocused by a mirror E, and it will be reflected to the exit slit F. So each wavelength of light is focused to a different position at the slit, and the wavelength which is transmitted through the slit G depends on the rotation angle of the grating. Okay, so in order to select the wavelength which can be directed from this monochromator to a sample or to a detector, we can adjust the angle of this monochromator, or we can change the positions, adjust the positions of the axis slit for the purpose of wavelength selection. One of the ways for the grating to select the wavelength is by tuning the angle. So different frequency refracted from the grating at different angle because of the interference at the grid of the grating. And this is the diffraction grating equations. M represents the diffraction order. Lambda is the wavelength of the electromagnetic radiations. D is the spacing between the grooves or the scratches on the grating. It is also equals to L over N, where L is the width of the grating and N is the number of the grooves, whereas theta is the angle of incident. Okay, this is the incident light which hit on the grating, and the alpha is determined from the grating normal, okay, to the directions where the light shine towards the grating. So this is the positions for the angle alpha, whereby beta is the diffraction angle for order M. Okay, when the light hit the grating, it will be diffracted. Okay, so the angle of these radiations diffracted is determined from the normal of the grating. Okay, so this is identified as beta. So this is the geometrical path difference between the light from the adjacent grooves. Alright, so the summations of this can be calculated using the equations here. So when the incident angle theta is equals to 0, meaning that if the light is directly shine towards the grating in these directions, then the theta will be 0. So the equation left will become m lambda equals to d sine beta. Okay. So this is how it further explained where is the alpha positions, which is the incident light angle, and the beta positions referring to the radiations which is dispersed from the grating, and what is the respective angle. Therefore, turning the dispersing element, it will cause the band of color to move relative to the exit slit. Okay, whereby the exit slit is at a fixed position, so that the desired entrance slit image is centered on the exit slit. The larger the photon energy, the smaller is the refraction angle. Okay, so basically the refraction angle for blue color is much more smaller compared to the refraction angle for the red color. Okay, so the range of the color leaving the exit slit is a function of the width of the slit. So if the width of the slit is wide, then it will allow a wider range of the radiations to pass through. You can scan this QR code and watch the video on how does the monochromator function. Similarly, this video shows how does a spectrophotometer works. This set of equipment was modified from an old spectrophotometer. And the component here is the diffraction grating. So basically, we can adjust the angle of this diffraction grating, so it will refract the selective wavelength of the radiations and direct it to the sample. This set of equipment is available and it is now displayed at the entrance of the Department of Chemistry. So if you have time, you can drop by and have a look with it. Besides, you can also try out on how does it operate. There is a poster pasted on the wall which is related to the explanations on how this spectrometer works. So you can play around with it. Whenever you have time, you can just try out by your own. Then you will have a better understanding on how does the spectrophotometer works. As we have seen the working of the monochromator, whereby an instrument that blocks all of the light except the light at a certain wavelength will be directed to the sample. Then the intensity of the remaining light is measured. The measured intensity directly indicates how much light is emitted or absorbed at that wavelength, where by varying the monochromator wavelength settings, the full spectrum can be measured. Rather than allowing only one wavelength at a time to pass through the detector, FTIR technique lets through a beam containing many different wavelengths of light at once to be directed to the sample or can be detected by the detector, and then they measure the total beam intensity. So this technology is also known as Fourier transform technology. In fact, Fourier transform is a piece of mathematical process which convert the raw data into the actual spectrum. So it allows us to convert a time domain spectrum to a frequency domain spectrum. The reason for the invention of this FT technology is due to the conventional method. By using the monochromator is quite slow in the process of measurements, and it can only measure the intensity over a narrow range of the wavelength at a time. So with this FT technology, the whole spectrum can be taken simultaneously within the required region at a short time.
Let's take a look at the fundamental definitions of the Fourier transform and its inverse. We begin with the Fourier transform equations, which is defined as, you can see from these expressions here. As I told you earlier, Fourier transform is a piece of mathematical expressions with the integrations. So here, the x represents the time, whereby the zeta represents the frequency. So this transform allows us to convert a time domain signal fx into a frequency domain representations. So next we have the Fourier inversion theorem, and this lets us reconstruct the original time domain signal from its frequency domain counterparts. This is a powerful relationship that shows the original function and its transform form a Fourier transform integral pair. That means there are two sides of the one coin, whereby one in time, the other in frequency. By understanding this duality is essential in the field like signal processing, where analyzing signals in both domains will provide a deeper understanding.
Fourier transform spectroscopy is a measurement technique whereby spectra are collected based on the measurements of the coherence of a radiative source. Using time domain or space domain measurement of the electromagnetic radiations or other type of the radiations. The two waves are said to be coherent if they have a constant relative phase. And this FT technology is applied to a variety types of spectroscopy, including optical spectroscopy, infrared spectroscopy, nuclear magnetic resonance spectroscopy, and so on.
How does the Fourier transform system work? It requires a system called interferometer to collect the data for the generations of spectrum. Interferometer consists of light source, beam splitter, two mirrors which are the fixed mirror and a movable mirror, and a detector. So the energy goes from the light source to the beam splitter, which split the beam into two parts. For the beginning of these explanations, we will focus on the monochromatic light as the source. The most important part of a Fourier transform spectrometer is interferometer. Instead of filtering or dispersing the electromagnetic radiation, an interferometer allows source radiations of all wavelengths to reach the detector simultaneously. So this is the setup of an interferometer with a light source, a beam splitter, two mirrors, detector, and there is a sample compartment which will be located somewhere here. Beam splitter is an optical device that splits a beam of light in two. So the light will come from the light source, split by the beam splitter into two directions. One is towards the fixed mirror, and the other one, the light source, will be transmitted through the beam splitter to a movable mirror. Beam splitter is the important part of an interferometer. In its most common form, it appears as a cube and made from two triangular glass prisms which glue together at their base using adhesive. The thickness of the resin layer is adjusted such that half of the light incident through one port is reflected and the other half is transmitted due to frustrated total internal reflection. How does this interferometer works in order to generate the data to be the input for the Fourier transform integral? So as you know, we have the light source, beam splitter, stationary mirror, and also the movable mirror. Lastly, we have the detector and also the sample compartment. Okay, so the light source will irradiate radiations to the beam splitter, whereby the beam splitter will split the radiations into two directions. It will reflect the radiations with 50% to the stationary mirror, and another 50% will be transmitted to the movable mirror. Upon arriving the movable mirror or the stationary mirror, the radiations will be reflected back to the beam splitter. Okay. When the radiations reflected back to the beam splitter, it will cause the process of interference to occur. Both of the radiations that will combine and they will interfere one another. So, after the process of interference, then the light, which is still has their intensity, it will be directed to the sample compartment and pass through the sample to the detector. All right. Now, how are these selections of the wavelength can be done? Let's say the movable mirror move away of d distance. Then the light beams has to travel an additional distance of 2d, meaning that if this movable mirror, okay, it is moved to a distance lambda over 2, a bit far from the beam splitter, from the positions of this red line to the positions of this blue bar. Okay, so what happened is that the radiations that transmit from the beam splitter need to travel an additional of lambda over 2 to the movable mirror. When these radiations reflected back to the beam splitter, it also needs to travel an additional lambda over 2 distance to the beam splitter. So by moving this movable mirror lambda over 2 away from the initial position at these red positions, where the distance between the stationary mirror to the beam splitter and from the beam splitter to the new positions of the movable mirror is no longer the same anymore. Okay, so due to the difference of the distance that both of these light travels, it will cause the optical path for the radiations to be different when they meet at the beam splitter for the process of interference. Okay, so with that, it will cause the radiations to select, or it will cause the radiations to be enhanced in the intensity through the process of interference. So just now we say that if we move the movable mirror to a distance of d from the initial positions, then the light beam has to travel an additional distance of 2d, okay, for towards and reflect back. So the total additional distance that the light needs to travel is also called retardation. Okay, so if the retardations is equals to lambda, is same as the wavelength of the radiations, then when the radiations reflect back to the beam splitter and combine with the radiations from the stationary mirror, it will result in the constructive interference. Now, if we move to another example, if the retardations is equals to lambda over 2, meaning that the total additional distance that the radiations need to travel is lambda over 2 from the beam splitter to the movable mirror plus from the movable mirror reflected back to the beam splitter. The total additional distance need to travel is lambda over 2. Okay, so we have to move the movable mirror a distance lambda over 4 from their initial position. At these conditions, when the radiation recombine from the stationary mirror and also from the movable mirror at the beam splitter, the interference occur, okay, will be destructive interference. It will cause the intensity of the radiations to be decreased. Now let's look into some example on the radiations, which is from the movable mirror, fixed mirror, and the radiations after they went through the process of interference at the beam splitter at different positions of the movable mirror. In this slide, if the D equals to 0 lambda, so meaning that the distance from the beam splitter to the movable mirror is same as the distance from the beam splitter to the fixed mirror. Okay, so if it is in these conditions, then the light which reflect back to the beam splitter will be traveling in this manner for this line here, indicated by the blue arrow, represent the radiations from the movable mirror, whereby the fixed mirror is indicated by the wave as this one of the green arrow. So when these two radiations they interfere one another, it will result in the interference, which is the constructive interference. So you will see that they will interfere and result in increase in the amplitude of the radiations. Okay, so the radiations of the light increase at the beam splitter, and this is the radiations which will be directed to the sample. So at the beginning of the experiment, when there is no difference in the traveling path, it will result in the very high response, okay, at zero change in the path distance. If the movable mirror is moved to a distance 1/16 part of the lambda, then you will see that the traveling wave from the movable mirror will be slightly moved. It will result in a slight change in the optical path. Okay, so when these two radiations recombine at the beam splitter, and it will result in the interference, something similar to this one. So you will see that the amplitude of these recombined radiations at the beam splitter is slightly lower compared to if there is no difference in the traveling path. If the movable mirror further move 1/8 of wavelength, okay, D equals to 1/8 lambda, then the total distance traveled from the beam splitter to the movable mirror and reflected back from the movable mirror to the beam splitter by these radiations will be an addition of 1/4 lambda. It can be represented by the curve, which is this blue line. Okay, so both of the radiations recombine at the beam splitter and interfere, results in the reductions of their intensity. Okay, so this peak and this peak, this point and this point, they interfere one another. So as a consequence of the change of the positions for this movable mirror, it results in the further reductions of the intensity for their response. If the movable mirror move a distance 3/16 lambda, it will cause a further change in the optical path difference compared to the radiations which is reflected back from the fixed mirror. And these are the profile or the wave traveling by the radiations from the fixed mirror, whereby this one is the wave traveling from the movable mirror at a distance of 3/16 lambda, okay, from their initial positions. So this again further reduce the response. The amplitude after these two waves interfere, it will further reduce in the amplitude. Okay, so the response is again become lower. Now, if the radiations is shines towards a movable mirror which is placed at a position 1/4 lambda, which is either nearer or farther from the initial positions, then it will result in the retardations of 1/2 lambda. The respective radiations which is reflected back to the beam splitter will appear in this manner. And these radiations is totally opposite to the radiations that is reflected from the fixed mirror. When these two radiations interfere, it will result in the cancel out of the amplitude. So the intensity will become zero. And this is the outcome of the destructive interference. Therefore, the photodetector signal will be dropped until zero. Similarly, if we move the movable mirror to 1/3 lambda, then it will slowly regenerate the response again. So it will result in constructive interference. Then we will see the appearance of the signal again. Okay, because they will have some value of the intensity for the radiations. So from equal distance between the beam splitter to the fixed mirror and beam splitter to the movable mirror with the highest photodetector signal, it slowly decreases until zero, where the destructive interference occur, and the further change of the positions, it will slowly increase in the signal again due to the path difference or the positions change allows the interference to occur, which is the constructive. So they will retain some intensity value. Therefore, we can get the signal. Okay, so the whole process will just goes on, and the photodetector signal will just go from maximum to minimum, after that to the maximum, and then to the minimum through the position change of the movable mirror. By now, you should have to know that the interference will cause the radiations to be disappeared in certain wavelength through the process of destructive interference. After the process of interference at the beam splitter, the radiations will be directed to the sample. Some energy will be absorbed by the sample and some will be transmitted. On leaving the sample compartment, the light is refocused to the detector. And the detector will read the information about every wavelength in the infrared region simultaneously. After that, it will plot a graph of power of radiations as a function of distance traveled by the movable mirror. Since we know the exact positions of the movable mirror and the speed of the movable mirror, The power of radiations can be also plotted as a function of time, and this pattern is known as time domain. However, the time domain will not be able to tell us the frequency of the radiations. Therefore, we need to convert the time domain plot into frequency domain spectrum. So it can be done by using the algorithm called Fourier transform, which is performed on the interferogram to convert it into a single beam spectrum. The information content in both time domain and frequency domain are essentially the same. Time domain graph shows how a signal changes with time, whereby frequency domain graph shows how much of the signal lies within each given frequency and over a range of frequency. So why use time? All data collected in single observation can be done, and it can speed up the process of data collection. Figure A shows the time domain graph, whereby figure B shows the frequency domain graph. Suppose we have a frequency domain spectrum that consists of two lines, each with a different frequency. The time domain spectrum of this would now consist of two waves, one for each of the frequency. The net time domain spectrum would be addition of those two waves. If there were many frequencies, then the time domain wave form would be a complex pattern. In the measurements of a sample using, for example, FTIR, a reference or background single beam is also collected without a sample. The sample single beam is ratio to the background single beam to produce a transmittance or percentage T spectrum. This transmittance spectrum can be converted into absorbance by taking negative log base 10 of the data points. The detector will process the data collected from the sample, and this is one of the example of the interferogram for the sample, and here is the interferogram for the background. Each of these will went through the process of Fourier transform calculations by the computer to transform this interferogram to become a spectrum. Okay, so they will ratio out and give us the transmittance graph or the spectrum. The transmittance spectrum can be converted into the absorbance spectrum. Okay, they are interchangeable. So in general, this is the flow of the FT equipments or FT spectrometer. We have the light source, shine the lights to the interferometer, which consists of the beam splitter and also the movable mirror as well as the fixed mirror. So the radiations will recombine at the beam splitter and interfere one another to result in the radiations which can be directed to the sample. The sample will absorb the radiations, and those which is not being absorbed will be transmitted to the detector. The detector will measure how much the beam is being absorbed or emitted. And this data will be processed by the computer to the desired results, which is the spectrum that we obtain. If the light source consists of two monochromatic light, which is slightly different in the frequency, combined to show interference pattern. At the beginning of the experiment, at time t equals to 0, the waves interfere constructively. This gives a maximum in the added plot. As time progresses throughout the measurements, where t is greater than 0, the waves get more out of phase and results in the destructive interference and decrease in the overall amplitude. The frequency of these oscillations is called bit frequency, which is the difference in the frequency between the two components of the waves. If the light source consists of two monochromatic light, then it will have two waves to be at different frequency appear. When these two lights combine at the beam splitter, it will went through a process of interference, and this is the ideal appearance of the time domain plot. In actual, the plot is something similar like this, okay? And their respective frequency domain spectrum after Fourier transform will become something like this. Again, this shows the radiations consist of two different frequency, one of it with one wave number, another one with three wave number. When these two waves act as the light source directed to the beam splitter and went through the process of interference after combined at the beam splitter from the movable mirror, the combined signal will look like something similar to this graph here. As more radiations varying in the wavelength involved as the light source, or if the light source is a polychromatic light, then they will have different types of the wave, okay, to be present, and it will go through the process of interference and results in this type of the time domain spectrum. So the interfering more than two frequency, in fact, imagine interfering hundreds of frequency together. Okay, as more wavelengths are added as the light source, the destructive interference takes place a large part of the spectrum. Example, if the light source consists of 1 to 5 wave number frequencies radiations, okay, when they combine, this is the outcome of the combined signal. If the range of the radiations increase to 30 wave number, which cover the wave number from 1 to 30, okay, and directed to the beam splitter, after that, it will be reflected and also transmitted to the movable mirror as well as the fixed mirror, followed by reflect back to the beam splitter and go through the process of interference. So this is the outcome of the interference, okay, for 1 to 30 wave numbers signal. And this signal will be directed to a sample in the sample compartment. If the sample absorbs the radiations at 10 wave number, and the radiations that pass through or transmitted through the sample to the detector will have a combined signal 1 to 30 minus 10 wave number. And this signal will be detected by the detector. And this is the appearance of the interferogram, okay, that reach the detector. If the sample absorbs the radiations at 10 wave number and 21 wave number, meaning that the radiation that can transmitted through the sample to the detector will have the combined signal 1 to 30 wave number minus the 10 wave number minus the 21 wave number. And this is the appearance of the interferogram which is detected by the detector. So from the detector, the computer will transform this interferogram into the frequency domain, which is the spectrum. Okay, so this is how the spectrum looks like for the light that is directed or incident to the sample, the incident light to the sample. And then this is the spectrum corresponding to the radiations which is detected by the detector. So at all the wave number, there is no reductions of the signal. At 10 wave number, there is a very drastic reductions of the signal. After wave number 10, then the signal increase back to their initial value, okay, until 30 wave number, which shows that the sample absorb this wave number. Therefore, the radiations at 10 wave number is become less when it reach the detector. So similarly, if the sample absorb wave number 10 and 21, then we will observe the appearance of these two peaks in the spectrum. This figure shows the simulated FT interferogram, which cover the range of the radiations from 1 to 3500 wave number. As more wavelengths are added, the destructive interference take up a large part of the spectrum. Okay, so this is due to the oscillation. Is the bit pattern set up by all the superimposed but slightly different frequency waves. The decay can be imagined by considering that initially all waves in the package are in step, but as time goes by, they start to be out of phase that on average they cancel out. Therefore, the rate of decay depends on the width of the original frequency peak or the frequency range of the light source. The broader the peak, large number of frequencies, the smaller the area of constructive interference, which means that the decay will occur more rapidly. If the radiations from 1 to 3500 wave number is directed to a sample which absorbs at this wave number, the appearance of the interferogram will be something similar to this one. So you will see that there is some difference when you compare these two interferograms. The signal detected by the detector generates this interferogram. It can be transformed into the frequency domain spectrum, which indicate the reductions of the signal or the intensity at the respective wave number. By now, you should have to know that how the interferometer works to generate the spectrum from a bunch of frequency which is simultaneously directed to the beam splitter, and the process of interference occurs to generate the interferogram, which can be transformed into the spectrum that we observe through the Fourier transform, which is the mathematical integration expression. And lastly, these are the setup for the instrument using the diffraction grating or the monochromator setup, as well as using the Fourier transform, which consists of the interferometer part in the instrument. So for these equipments using the monochromator, The diffraction grating need to be tuned angle by angle in order to achieve the required wave number or the wavelength to be directed to the sample. It takes a very long time for the measurements because it takes time to tune the angle. While for the Fourier transform, it can process the data by having the data produced by the interferometer, where the light source direct the radiations in a range to the beam splitter to generate the interferogram. So these are the components that are required in the equipments, either using the monochromator or the interferometer as the wavelength selector.